Good evening. Welcome back to another Watson lecture at Caltech. I hope you guys had some fun with our pre-show. I heard some pretty great jazz music, and I saw a food truck. Maybe you saw some displays by the Seismo lab or met an earthquake fellow. Yeah? It was pretty fun, right? Wonderful. So the Watson lectures are in their 101st season. And I just want to take a moment to thank all of you that, okay, maybe not come every year, but at least every month to our lectures. And if this is your first time here, welcome. I also want to take a moment to give a special welcome to the students of South Hills High School in West Covina. As this month's members of our Junior Watson program, they got a chance to tour some labs, and of course we told them all about the great opportunities to study science and engineering here at Caltech, right? You're all coming? Okay, okay, great. We'll see you next year. I'm Crystal Dilworth. I'm your host tonight. I'm a science communicator and a Caltech alum. And in the time that I spent here in doing research with Henry Lester on the molecular basis of nicotine dependence, I learned what it meant to be a scientist. And being a scientist doesn't just mean contributing new knowledge through scientific research. It means being able to explain how a single atom substitution in a single subunit of a single protein receptor complex that's only expressed in some layers of certain brain regions contributes to a greater chance of dependence and lung cancer to those that carry the mutation, and contributes significantly to the leading preventable cause of death in the world. Now, I've built my career on being able to communicate how the work that's done in the laboratory impacts our everyday lives. And I mean, hosting the Watson lectures on the one night a month that Caltech opens its doors and welcomes you, the public, in to talk about the really cool stuff that we're doing is one of my favorite ways to do that. So I'm super excited that you guys are here tonight because we are celebrating Earth Week. Earth Week. And believe it or not, Caltech actually has a really long history of contributing interdisciplinary approaches to answering questions about climate and pollution. So, for instance, in the 1940s, there was a geochemist, Claire Patterson, and he made a connection between lead pollution and automobile exhaust. At about the same time, his colleague and my favorite historical faculty member, Ari Hagenschmidt, was also making a similar connection between automobile exhaust and smog. Now, these discoveries were so transformative that it eventually led to Dr. Hagenschmidt serving as the first chairperson when California formed its Air Resources Board. So I don't know if any of you were living in Los Angeles before the air quality regulations, but talk about impact on daily lives. I mean, hey, we can all breathe. Of course, Caltech's contributions didn't stop there. Another geochemist that was trained here at Caltech created the first instrument to accurately measure carbon dioxide in the air. John Seinfeld, another faculty member, created the first model of an urban atmosphere. Biologists and geobiologists Diane Newman and Victoria Orphan told a story about how microbes contribute to the Earth's evolution and climate. And Nobel Prize-winning chemists Francis Arnold and Bob Grubbs created molecules and catalysts that make chemical products like detergents and medicines and materials more green. But tonight, we're going to hear about the work of Professor Zhongwen Zhan and how his research on the physics and the deep structures of glaciers and ice sheets in Antarctica are helping us to understand how Earth's polar regions are changing due to climate change. Now, of course, before we hear about his research, we're going to hear a little bit about Professor Zhang, the person. So there'll be an introduction by the chair of the Division of Geology and Planetary Sciences, and then a short video that'll tell you a little bit about his life and his work. After his talk, That's when you guys get a chance to ask your questions. So what you're gonna do is you're gonna use your phone to follow the link on the QR code that will be displayed here. That will take you to a platform where you can upload the questions that you have for me to ask Professor Zhang. Now, if QR codes aren't your speed, that's totally fine. Just raise your hand, and we've got friendly ushers in the back that will come with a comment card so you can put your questions down there, and they'll make sure it gets uploaded to me. All right, well, I think that's all of the business. So if you will take this moment to quiet your cell phones, your watches, any of your technology that could potentially make noise, note your nearest exit, and please help me welcome to the stage the Division Chair for Caltech's Geology and Planetary Sciences Division, Dr. John Grotzinger.
Good evening and welcome. It's a pleasure to see so many people out here in the audience, and it's also my pleasure to introduce my colleague, Zhongwen, who is a really wonderful colleague and scientist. The greatest pleasure of being a division chair is helping to hire and support the young faculty, because they come in with tremendous enthusiasm and a wealth of ideas, and all you have to do is find the resources for them and get out of the way. And in Zhongwen's case, it's been a particularly fun relationship for me as division chair, because he's unusually enthusiastic, as you're going to find out, and especially creative. And this was somebody that I would meet with once a year, and he'd always be thinking about something different. And I remember my first experience with Zhongwen when he had just somehow figured out to work with the city of Pasadena to get access to the fiber optic system that goes around the circumference of the city. And then from that, he looks at noise. And in his form of geophysics, he basically parses into two flavors. One is to look at the dynamics of deep subduction zones, and the other is to look at the ambient noise that the Earth makes at all different frequencies, and from that derive signal that tells you about the Earth processes that you'd like to learn about. Now, in this case, he came to me and showed me a data set that he had collected on January 1st of the floats moving down Colorado Avenue. This was amazing to me, because you see the floats, they're impressive, but yes, they have mass, and yes, they deflect the Earth, and they move along, and they propagate a wave, and he was able to detect that. Not only that, but he was able to tell you how big, how massive the float was, and I thought this was marvelous in the literal sense of the word. And then another year went by, and he came to me and he told me that he was working with Google to try to get access to a fiber transoceanic cable that runs between LA and Santiago, Chile. And there was a couple of technical hurdles involved in this that I was confident that he could figure out. But the harder part of it was to get permission from the FCC to operate on that cable, and it was even harder to get permission from the Navy to utilize that cable. But we had a trustee who was the former chair of the Joint Chiefs of Staff that was helpful with the Navy. And it turned out that my cousin was the chief lobbyist for Disney and knew who to talk to at the FCC. So they both came to Caltech, and we stapled this together, and he eventually got access to that. But I think my favorite example of this was something that I didn't know, because it was him sitting and doing theory with another young colleague who hadn't got tenure yet, Jorn Callies, who's a physical oceanographer, and the two of them realized that if they pulled their skill sets, that you could utilize the SOFAR channel in the ocean, which is this low velocity zone where acoustic waves will travel at a much slower speed than the rest of the oceans. This is where whales figure out how to signal to each other over thousands of kilometers. This is where the Navy learns how to listen to submarines long ways away. And what they realized in this case was that the velocity of acoustic waves is dependent on the temperature of the water. But this is a very, very difficult measurement to make. And by the way, the world won't let you blow up dynamite anymore to create an acoustic wave to measure how fast it moves. So what Zhongwen was able to figure out was that there's a class of earthquakes that are called repeating earthquakes. And once you identify these sources, you can depend on them to send a signal at a relatively frequent and regular basis. And then from that, you can then create a time series of data that shows how the velocity field is changing with time. And then with some clever theory on the part of Urankalis, you can then single out temperature and demonstrate that the deep oceans are in fact warming due to climate change. So I think with that, it is my pleasure to introduce Zhongwen, and I'll turn it over to him.
I grew up in eastern China, really the countryside, so there's a lot of freedom. I don't need to do much classwork. I just play most of the time near the river, in the mountains, so it was a fun time. You got to observe the Earth, which turns out to be what I'm looking more closely now. I'm Zhongwen Zhan, professor of geophysics. My group studies seismology, especially using fiber sensing to get more information out of the Earth. I entered college at a pretty young age, 15 years old. There was a new professor joining my university at the time. He got his PhD from Caltech, the Seismology lab. So he joined the university and gave a wonderful lecture about what scientists are learning about the earthquake. And then he recommended me to his PhD advisor here, Dan Hamburger, and that's where I did my PhD. Seismology is a very broad topic. You basically listen to the sound from inside the Earth. Recently, I have been focusing more on using it for environmental research. How the groundwater in California is going up and down due to the drought, how glaciers move, and how that would impact the sea level rise. I have been trying to convert all those telecommunication fiber cable that provide you high-speed internet into seismic sensors so that it's a much faster way and affordable way to have a very dense array. The conventional seismic sensors, they are basically individual device. You dig a hole, you bury them in, and they sense the ground shaking at that point. The fiber sensing approach, by connecting this fiber sensing instrument on one end of the fiber and turn every meter or every 10 meters of the fiber into a sensor, and the density along the fiber is very high compared to conventional sensors. We do sacrifice a bit of sensitivity, so we don't sense as weak of a motion that conventional sensors can sense, but it's a completely new type of data. You can see things you couldn't see in the past. And from that moment, we basically couldn't stop. The data is so beautiful, we're seeing a lot of beautiful results, and we're starting to expand into many other areas in California and beyond. The South Pole trip certainly was a transformative one to me personally. You suddenly switched from a busy kind of juggling many ball kind of environment to a vast, wide continent. You reach this state of Zen and focus on the challenges you have to face in fieldwork. That helped me regain the kind of passion about research itself. The Earth is constantly making sound. By listening to the Earth carefully, you can really learn a lot about the Earth and all the different processes. And I think there is a lot more to be done. Thank you. Thank you for coming to tonight's Watson lecture. It's really exciting to see all of you tonight.
I listened to many Watson lectures before, and I always learn a lot. But tonight, I want you to sit back, relax, and listen to a story I have to tell you. It's a story about this trip I made to the South Pole, Antarctica, and I'm going to tell you what I did there. I'm not much of a social media person, but during the trip, I decided to post, photos of how scientists do research as a kind of science outreach activity. I post many photos, but this one everyone loves. Also appeared in their video a little bit earlier. People are just wondering, like, why is this scientist hammering ice in Antarctica? Isn't science always with a lot of high technology, electronics, and so on? I hope by the end of the talk I can convince you that sometimes scientists need to use a little bit of brute force as well. Okay. Before I get to that, just a little bit of a backstory first. I'm a seismologist. I guess when you hear about seismology, you may say, oh, that's earthquake science. You do earthquake research. Indeed, that's a lot what we do. You may know famous seismologists like Charles Richter, who defined the Richter magnitude, and Lucy Jones, our earthquake lady. We tell you what happens after earthquake, and we try to do better in prevent the hazard. But seismology is really broader than that. It's really about, I think it's a science that you listen to the voice of Earth. The voice can be coming from earthquakes, but it can be coming from many other things. John was mentioning the float, and your car driving around can make noise. The ocean waves, the wind, all kinds of processes can generate seismic noise. And we have more sophisticated way to understand how waves propagate inside Earth and figure out what's happening there. Not only just about the earthquake themselves, but also about what's the structure of the Earth, how do they move in time. It's pretty much like the case of a medical imaging, right? These days, medical imaging is doing really, really well. This is a particular case of X-ray. So you have a source, the rays go through your body and then get detected by a very dense array here. Not only that, they turn the machine so that they can look at you from all different angles. That's how you get a really clear image of your body. And we, seismologists, want to do exactly that. And we want to have a lot of sensors out in the world to detect what's vibrating. And this is the kind of sensor we use. We have a very good world-class seismic network in California. This is proudly operated by Caltech jointly with USGS. Every triangle here is a seismic station, and they look something like this. So their actual device is actually buried underground, so they can sense the vibration. But you have all this electronics and solar panel to provide power, data telemetry, and so on and so forth. So it's an effort, and we have one of the best network in the world. That's why we have earthquake early warning and all those other informations about earthquakes. But if you see, this is pretty dense, but we kind of plot the symbol very big, right? Like if you zoom in say, Los Angeles area, now you can see the red triangles are not that big, right? They're not that dense. They are kind of separated around 5 to 10 kilometers, a few miles apart from each other. It turns out there's a lot we want to learn even between those sensors. So they're still kind of too sparse. And we hope to have more, but those sensors are pretty expensive. Wouldn't it be wonderful if, let's say, I draw a line here from Griffith Park to Long Beach? What if we have 5,000 sensors placed on that track every 10 meters? Wouldn't that be better, right, than what we have? We did exactly that. This is what the data looks like. So this figure here, horizontal axis here is from 0 to 5,000 sensors. Left end is Griffith Park, right end is Long Beach. Vertical axis here is about 30 minutes time. Later is here, earlier is here. And whenever it's quiet, it's showing as blue. Whenever it's noisy due to vibrations, it's showing as red. And every one of those little yellowish lines is one car driving on that road, causing vibration, and our sensor can detect them. And we can track them. We can even know if you are speeding or not. And this big yellow band here, going from Union Station to Long Beach, that's a cargo train. It's very long and heavy, it's very noisy, going pretty slow, right? I can detect that very clearly. And then you can see there's a little horizontal line here. If it's horizontal on this image, it means that it's propagating through the entire area in a couple of seconds. Well, cars cannot do that. That is an earthquake wave. This particular earthquake was a magnitude 3 earthquake underneath the Seismology. And we can detect them traveling across the entire area basin. This is the power of this kind of dense array. If you have only a few traces here separated by a few kilometers from each other, you can never tell what's the difference between them. But suddenly, by looking at this image, it's very clear what's going on. How did this technology work? How did we suddenly have 5,000 sensors? Well, it turns out there's no magic. This red line here was they're called Alameda Corridor with the train station. And underneath there, they actually buried a fiber optic cable for telecommunication purpose. And we use this distributed acoustic sensing technology, I call it DAS. We connect a unit of equipment to this cable that's already underground. And it will turn every meter of the fiber into a sensor without actually going there, putting a sensor. So it works by sending a laser into the fiber and then listen to the echoes. Well, why would there be echoes? It turns out the fiber, even though it's manufactured to be really good at propagating light, there's still a small amount of defects inside. So the light propagated there, and they will scatter very tiny amount of light back. So we send the laser pulse, and we listen. And we hear an echo from those defects. A moment later, we send another one, we hear another echo. Well, we can see if that's the same or different. If the Earth is vibrating, the cable has been stretched and bent, well, the echo will be a tiny bit different. And we can actually detect that to figure out if that cable is actually vibrating or not. Since the defect is a manufacturer thing, it's almost everywhere along the cable. So now I can take every 10 meters of that cable and treat it as an equivalent sensor. So that's how we suddenly have 5,000 sensors just by putting that machine on the end of the cable. Since this method is, as long as you power this end of it, it's actually continuous and it's going to have real-time data flow. So this is wonderful news for seismologists. We always want that. And another wonderful thing is the fiber is nothing special. You are using the regular telecom cables that's already in place, the same cable that provide you the high-speed internet. Now let's think about the potential impact of that. This is the California-wide map. These are the conventional stations we have. It's pretty good. But now I'm overlaying on top a fraction of the fiber network we have in place. Just imagine what we can do with this. Every 10 meters of those lines, along those lines, become a seismic sensor. It's going to be about 1,000 to 10,000 times more sensors than what we already have. Right? I wish one day we can do all of that, but we already started. The red lines here are the arrays we already did. We actually started from deep in the Mojave Desert with the JPL fiber, also in the city of Pasadena, the one I used to look at the floats. And then we expanded further into area basin, offshore, and also particularly along the Eastern Sierra. We now have quite a few arrays. And these arrays are generating hundreds of terabytes of data already. And by looking at this data, we were able to image the interior structure of the Earth. This is the cross-section through the Long Valley caldera in the Monmouth Mountain area. We also use it to image how earthquake rupture. We even rushed to deploy something after the 2019 Ridgecrest earthquake to catch some of the aftershocks. We know that's when earthquake happened. And we sometimes look at the flows. And the most fun part of that is actually to figure out which band was marching the loudest. Because when they are in perfect synchronization, they cause a lot of vibrations. So we can definitely tell who is the loud one. Okay, so as you can see here, you'll probably agree with me that there's a lot more work to do here, right? Like, there's a lot more science we can do here. So why Antarctica then? I still love California, okay. But why do we go to Antarctica, go to a faraway place? It turns out Antarctica is really important for the whole Earth and also to people in California. It's the driest, the coldest, and the highest continent on Earth. 19% of all the ice on Earth are in Antarctica. It turns out it's so massive, if you melt all of them, the sea level is going to rise by about 180 feet, right? Fortunately, that's not like all of them are vulnerable, right? But we really want to understand how much of the ice will be lost to the sea. And the small uncertainty, because of huge volume, the small uncertainty in understanding that process leads to very large uncertainty of sea level rise. And a big part of the uncertainty coming from what's happening underneath ice. We have better and better satellite observation from the top. We can see the surface. But there are kilometers, miles of ice, and it's hard to tell what's underneath. I hope by now you realize that seismology is the best tool for doing that. We know how to look into the Earth. We can look into miles of ice with the seismic waves as a tool to image what's happening underneath. I'm not the first one to come up with the idea. This is why Antarctica seismology has been going on for decades. But there are challenges. If you want to do seismology, you need stations and you need sources. And it's hard to come by either one in Antarctica. This figure here shows the seismic stations in California, in Antarctica. You might say that looks pretty good. First of all, that's the size of the United States, and there are less stations there in California. Second, all the orange triangles are actually temporary stations. It's such a cold and harsh environment, seismometers only survive one season. Right? If you really want to see how things are changing over time, you want them running all the time. It turns out the continuous stations are only the green ones, and you can see they're mostly on the edge, slightly warmer part. In the entire interior of the continent, there's only like one sensor that is at the Amundsen-Scott station at the South Pole, and it's a US-maintained station. It's very important, but it's one of them. This is how hard it is to do field work in Antarctica. You fly a group of people in with a lot of equipment, and you start digging, okay? And you put a solar panel, you bamboo, so the next year you can find it. The next year you come to pick it up, you need to dig an even deeper hole to get it out of there. So it's pretty precious data that we use very carefully. But this is where I think fiber optic sensing, the DAS technology, can make a big difference. Fiber sensing is able to do permanent, continuous operation as long as the cable is out there. I only need to care about the one end of it. And that's a wonderful thing for this kind of research. So we decided to try it. No one has done it, so we say, let's find a way to test, see if this idea would work at all. Well, for the first pilot project, I don't want to do something too complicated. I don't want to bring a ton of cables there. I said, is there a fiber optic cable already in Antarctica? It turns out there is, kind of crazy. So this is the Amundsen-Scott South Pole Station. There was a seismometer there for a long time, for tens of years. But then there are so many people come to South Pole to do research. It's getting so noisy. People are pretty noisy. And they say, this is too noisy. We need to move this station away. So they move this station 8 kilometers away from the South Pole Station. And if they do that, they need to power it. They need to get data back. They actually installed, the other people did the labor. They installed 8-kilometer cable by trenching on the snow. It's hard work, but the fiber was in there. And 20 years passed, I got to know this cable. And the cable is now buried by more than 30 feet of snow. It's the best possible way of coupling the fiber to the ice. So we said, let's do this project. And that's what we got funded to do. It was delayed for 3 years due to the pandemic, not surprising. But finally, we got to go in the day before Christmas, I believe, in 2022. And we took a long trip to get there. You first fly to Auckland, Christchurch, McMurdo, and Amundsen-Scott Station. It's like a 10,000-mile trip. It took us 12 days. It's almost all by airplane. So why did it take so long? Like we have to quarantine almost everywhere, from home, New Zealand, McMurdo, South Pole, and there was many cases where we're like, we're probably not going to make it. We hear horror stories of other scientists. They got all the way there, get COVID, and get sent back home without doing any science. But fortunately, we were pretty lucky. We did everything we wanted to do. And maybe a slightly better part, okay, this is actually the airplane we took. It's a military airplane, the Hercules, except that they changed the wheels to sled so that they can land and take off on ice. And this is the interior of that. I don't know if you consider this economy class or, you know, well, the seat is, you know, you strap yourself to a mesh, that's all. But given the free luggage we are allowed to bring, it seems to be pretty good. There is actually one first-class seat in this, which is that soldier is sleeping on the cargo. That's where you can lay down. So that's good for him. So then we got to McMurdo. The good thing is that even in your quarantine, they are pretty free. Like as long as you don't mess with the staff there, you can go outside to explore the nature. This is actually the McMurdo station. It's a station that is the largest one in Antarctica. It can host more than 1,000 people in the summertime. And this is actually the Discovery Hut. This is where Robert Scott, the explorer, right? He always started from here to his trip expedition into the interior Antarctica, including the one went to the South Pole. So this is the mountain Erebus. It's one of the active volcanoes, actually not too far away from the McMurdo station. It's a very spectacular view there. And then after a few days of tourism, we get on the airplane again to fly to South Pole. This is the mountain we need to fly over. On the way there, this is when we fly over the Biedebach Glacier. This is the glacier that is feeding a lot of the ice from the interior Antarctica flow into the lower places, like the ice shelf places. You can see this is a pretty difficult terrain. Some places covered by snow. Some places very shiny with a lot of crevasses, very big cracks on ice, blue ice sometimes. It turns out this is the same truck Scott was pulling, the team was pulling by man their cargoes, their equipment to South Pole. This is the same trip that they eventually reached the South Pole, but a few days later than Amundsen. And then they come back along the same track, eventually didn't make it back to the Discovery Hut. They all died on the way. So at that point, I wasn't definitely complaining about the airplane. Like, it's a huge privilege now. We are able to get on an airplane with tons of cargoes, equipment, and being able to do the experiment that we want to do. It's really a privilege that we have today. When you get to the South Pole Station, this is actually, we don't live in tent. South Pole Station have a pretty big presence. This structure here can host more than about 140 people in the summertime. And there are even like 40 people living there in the wintertime to take care of everything. And there are actually Caltech students and postdocs there doing their astronomy and astrophysics research using the telescope there, using their neutrino detector there. So the cable was already in place, but we still have to go out there to deploy some, sensors that we know about, just as a calibration of if everything is working. That was not too heavy work, a couple of hours, but after that, this is what it looks like, right? It's like all your hair is, like the air, the moisture just freeze on your face. You really have to be completely covered up doing the field work, especially if you're on those snowmobiles. The wind chill can be terrible. But fortunately, we don't have to do all the cable deployment. Most of the work is actually in this little computer room to the right, where the cable comes into the station. All we did was to stack up this equipment, connect them to the fiber, and turn on, and suddenly we have, a couple thousand sensors. In this case, we were doing every meter, so it's 8,000 sensors. That's already like a single experiment, a few times more than the entire number of stations in the entire Antarctica over the years. We have a lot of hard drives. We actually produced 200 terabytes of data over the year. So this is the moment when we got the first data. This is the same plot as I was showing you for Los Angeles. except that it's all blue. There's absolutely nothing going on out there. So now it's 8,000 sensors. There's actually a little yellow band over here. This is when the cable go from the computer room over the roof of their power plant. And the generator inside was like vibrating like crazy. So we detect all of that. We actually was telling them like one of the machine was not doing well, like the noise was different from before, right? So this was actually a Sunday evening when we finally get everything running. It was small problem here and there, like always in the field. But we eventually get it working. This is about 10 p.m. Sunday evening. And at that moment, I know this is going to be a success. It is working. Okay, I could just wait there for natural earthquake to happen, but I know there's not many of them in Antarctica. As one of the figures show, earthquakes are mostly outside. So I actually was prepared. I brought my own seismic source. Okay, so I brought a few different ones. Okay, I have a hammer. I have a bigger hammer. This was actually like, the piston was about 40 kilograms. And I have some small explosives that you can put in the front of this, what's called a seismic basic gun. But you dig a hole, you put it in, and you fire it. It's a blank shell, basically. There's no bullet, but causing a small explosion. In our California experience, this one, the wave would be detected about tens of meters away. If you do this one, you can see them hundreds of meters away. We know there is about 3 kilometers of ice on South Pole, and we need this. This was more like kilometers away, thousands of meters away. And this is a test I did on Caltech campus. I hope no one blame me on that. So you have to actually have some weight to hold it down. Otherwise, the gun will fire off or fly away. Actually, that wasn't supposed to happen. It's called a blowout. The energy should go down, but it didn't work well. It's a good video. Okay. At that point, that Sunday evening, I actually don't have this yet because it's explosive. It took a long time to ship. When I was at South Pole, that explosive is still in Los Angeles. This one, I need to wait for the next morning for the people to give me the piston bullet so I can drive it out. But I have the hammer. I cannot wait. I just grab my hammer and I go outside. I started just hammering like crazy. I think I hammered about 49 times or something like that. It may feel like that's easy, right? It's actually not easy at South Pole. First, it's 9,000 feet. Like you cannot catch your breath after a while. And second, it's extremely cold outside. You first go outside, you're freezing. And then the moment that parka is warm, it's like you are completely sweaty inside. Like after like 40 times, I'm done. Like I'll say, go back and check what the data looks like. The good thing is we can see the data in real time. And this is what the data looks like. This is now 3 kilometers, right? That's like a little bit less than 2 miles. This is time. I'm a hammer over there, and you can see the seismic wave propagating. You can still kind of see it even over this corner. I can see the wave on the cable 3 kilometers away. In California, using the same hammer, I can do at most 100 meters. Like, why is it so good? We were so excited. I think the reason is that the cable just perfectly buried in the snow. It was just so quiet out there, nothing's going on. And the ice there is so cold, it's so rigid, that the wave doesn't really attenuate, just propagate without attenuation. It can propagate really far away. So we were like, this is great. We're going to bring the big hammer tomorrow. And we go out there, and we look at our hammer, it looks like this. We installed it the day before, and by this time it's completely frozen. It's like the piston is frozen within the pipe. It would not move at all. We were using torch guns, we were using hammers. We spent hours on it until we break it free. And then we moved out to hammer to do some tests. And another problem happened. The snow is so fluffy, the plate underneath disappeared after like 20 strikes, and we couldn't do it. Well, that's the only big source we have. We said, okay, let's do it. Let's just go out and hammer every location 20, 30 times and move on to the next one. We're going to hammer like crazy every 100 meters over that 8 kilometers. And that's what we did. And we put this thing on the back of this piston buoy, we're just driving, stop at the location, hammer it, and then we move on to the next position. The plate, that metal plate, like usually in California, I would just hold it and walk. There it's heavy, so I have a cable dragging it behind the piston buoy, and once we stop, I go out there, I push the plate down underneath the piston. The plate actually have a little cable connected to a GPS sensor, so every time I strike the plate, it will detect exactly where and when I strike it. So I can go back, look at the data later. And then we just, stop and then strike until the plate disappeared, and then we move on to the next location. Yeah. And you can actually see visually like how the plate is sinking into the snow pretty quickly. It sinks a little bit slower and slower in the end. We look at this data, go back, we were excited. We actually have terrible data. I couldn't see it, even very far away. And we were very confused, like, did I just getting stronger when I swing hammers? Was that just more powerful than this? It turns out that's not the reason. It turns out the reason is the noise was different. I was in a Sunday evening and no one was out there. And this is the noise at the South Pole. This is the morning working hour, very noisy. They have lunch, quiet. And then afternoon they did work, they're getting tired, I guess. And then they have dinner, very quiet dinner time. But South Pole is always daytime in summer. So they go out to do more work until they have their midnight break. And then they did more work. The first night I was doing it was a Sunday evening, no one was working. But the next day I was going out, everyone's working. So I left with no choice. My field time just getting a lot shorter. I thought I can hammer all day. It turns out I can only hammer when they are eating. Well, the South Pole is not a normal place. You can just go to a restaurant anytime. The galley only opens a certain time. So what do? Well, it's always daylight. At least that part is good. We sometimes go out 3 a.m. in the morning, but we pack our food. We do our work. When they are working, then we eat, right? And we do that. And the piston buoy actually have some air conditioning, but it's still very cold. So we're eating cold food all the time. Not pleasant. But except the ice cream. You just put it in the back of the truck. It stays good, very good. Okay, that's the happy moment of those field work. Okay, once we do that kind of hard work, it's beautiful data. Now you can see this is 8 kilometers all the way to the far end. This is where we're striking, and you can see the energy very strong there, and it's propagate. You can now see them all the way to 8 kilometers away. How far is 8 kilometers? Well, if I put that hammer here in this auditorium, and this would be a radius of 8 kilometers. So if we are at the South Pole here, if you live anywhere within this circle, and I hammer the ground, you can hear it. Can you imagine that? It's just hammering, right? Like, it's just such a quiet and quiet place, and the wave propagates so far away. Not only with that high-quality data, we can see the wave propagation. This wave almost sounds like music. Definitely sounds like music to me, but it literally sounds like music. On the left figure here, this is not my data, but this is someone playing do, re, mi, fa, sol, la, si, do. Right? Frequency goes up. And you can see there are other harmonics of the fundamental mode, right? If I take my data, because I have such a dense array of data, I actually can also do the same thing. I can look at the frequency and how fast they travel. And they have all these harmonics in there too. I actually can see 16 modes inside there. So if you're thinking about a musical instrument, it's like a wave trapped in a pipe, for example, or on a string. So what is the trap in the wave here? Turns out in this case, the wave is being trapped by this snow layer. So you have snow on top, you slowly compact them into ice. So on the top, there is 100 meters of snow. That is a little bit less dense than the ice and a little bit less rigid than ice. And the seismic wave, they just get trapped within this layer. So this is like a natural instrument with all these different modes propagated inside. And once we realize that, we can find a model how the ice velocity increases as a function of depth to about 120 meters into it, so that I can match almost every one of those modes, right? All those harmonics. So this is basically the highest resolution constraint you can get for how the snow is being compacted into ice, right? And also in the South Pole, there's not too much going on with this snow layer, but everywhere the firn has a different behavior. In Greenland, sometimes they have water in it. And it's really important to understand what the firn layer is doing in climate change. This firn layer is a sort of like a blanket for the ice. When you have temperature change, you have precipitation, this is the layer that protects it. It has to go through this layer before it reaches the ice. Actually, scientists find that it's often this layer that gives you the earliest signs of the impact of climate change to glaciers. So we hope this method can be used more often in other places, not only just in the middle of Antarctica, but maybe on the edge of Antarctica, in Greenland, and other places. So this is going to be really interesting already. But I said in the beginning that we want to look at the ice, right? We want to look at some deeper structures. So how did that go? Well, the problem we are looking into is what's the temperature at the base of ice. You can imagine that you have a piece of ice sliding or moving, sitting on this continent, try to slide into the ocean. If you have a bed that's cold, then the ice is essentially frozen to the rock. In that case, if you want to move the ice, you have to deform it, and that's a slower process. If you have a solid bed, then you would have a wet sediment sitting underneath the ice. Now the ice not only can deform, they are sitting on a pretty slippery slope, and they can move a lot faster in that case. And we really want to know what's the temperature distribution over the continent. Turns out we actually don't know that. The figure to the left is from a model. So from modeling, people try to guess, okay, what would be the basal temperature over the continent. The only thing you can say is, well, it's very complicated. Very nearby place, sometimes they think it's frozen, sometimes it's sleeping. And if we talk to any glaciologist, they will say, you do not necessarily should trust this. We need new observations. Can we do this with seismology? That's what we're supposed to do. The way we can do this is looking at a seismic wave that is bouncing from the base of ice. If the bed is frozen, or the bed is on a slippery, wet sediment, the echoes we're going to hear from that bounce is going to be slightly different. As long as we can detect this reflection, we can figure out if the bed is wet or frozen. So that's going to be the goal. And that's why I want to bring the explosives, right? Because there is like 2 miles of snow there. My hammers, the wave cannot propagate that deep and get bounced back, especially in the place that keep disappearing in the snow, right? So only about 3 days before I had to leave South Pole, finally the explosives arrived. We were very excited. We go out there and we start to do the experiment. We have things to hold it down. And it's supposed to be good, right? Nothing blows out. Does that mean the energy gets propagated very nicely? We went back to look at the data. It was, again, terrible data. It was even weaker than my hammer strikes, like even single hammer strike. It's supposed to go kilometers away. Why didn't it propagate? So we go out there, we dig out where we just fired the shell. We found that it exploded a little hole there. So the snow is so fluffy there that the explosive used all the energy to push the snow, to compact the snow. Make a big hole there, wasted all its energy. Nothing was going to propagate as the seismic waves. And we will only have like 3 days left. We tried all kinds of things, nothing is working. And we were living with 2 choices. One choice is give up. There is actually cross-country ski available there. You can choose to spend the next 3 days cross-country ski. But I thought maybe, I don't know what's the next time I'm going to come to the South Pole. I cannot let that happen. This is the most important target of the experiment. I need to see the reflection. I only have the big hammer, but the plate keeps disappearing. So we decide to find a location, and we're going to hammer until the plate disappears in the snow. We're going to dig it out. We're going to backfill this hole with snow manually, and then we're going to do it again. And then we're going to do it until we hit the same spot 1,000 times. And I hope by stacking 1,000 shots, 1,000 strikes, I will see the signal. There's no guarantee of that, but that's the best I can try. I spent the last 2 days with my friends, just go out there and digging, like hammering, and fill back the snow, wait, and until people start working and we cannot do it anymore. We actually, get beautiful data from that. Now you can see the wave propagating very nicely. You actually can see some energy here now. These are actually some of the body waves propagating in the snow. But, there need to be more further processing to know if the reflection is actually there. It's actually buried underneath there. So we left the South Pole with a little bit of uncertainty in our mind, to be frank. Okay, we didn't know if everything was working. But once I got back, my students started to take the data, and we did a filter onto it, and you can see this little energy over there. That matches exactly where the reflection is supposed to be. We were so excited, totally worth it, right? And another way to look at this is we can look at the amplitude of this wave here. And there's a peak of energy at exactly where the supposed reflection is coming back from the base. Very strong signal there. And I asked my students, I said, what if I didn't do it? I kind of regret I spent so much time just digging and backfilling the hole. What if I didn't do it? And he showed that if I didn't do it, this would be the noise. This would be the signal I got. I basically, by hammering 1,000 times, reduced the noise from here to here by a factor of 10. And that's what allowed me to see the reflection signal. And now with this reflection signal, our initial result shows that the base of South Pole is actually wet. So this is a place the snow, the ice is freely sleeping at the base. So it's one of the less favorable scenario in terms of ice dynamics. So I want to get your attention to the amplitude here. What does this mean? 10 to the minus 9 string. This value means the amplitude of this wave we are looking at, as we detect them on the cable, it extended this 8-kilometer cable by about the length of the thickness of your human hair, right? So that 8-kilometer cable just become 50 microns longer. And we were able to use this technology to detect that and tell that there is a seismic wave bounced back from the base. Right? So this is really exciting. This is a particular thick ice, and it's not a favorable source. We believe this means we can go to other places, bring better source. We will be able to image the glacier base at a much higher resolution than what people could do in the past. So at that point, we had to leave South Pole. And as I said in the beginning, I hope that this technology can be continuously operating in Antarctica. Well, our machine was in this computer room with perfect power and the air conditioning and so on, right? It never got cold. So we decided to leave the machine there, let it run for the whole year. We actually only get the data back just a month ago or so, right? And it's a lot of data for us to crank through. But it's really amazing because initially when we think, we say, okay, we want to see how the ice is changing. Does that mean we have to go out there, hammer ice every week or every month? I'd like to do that, but my wife would not let me, I'm sure. So we need to find something naturally happening there that can tell us what's happening under there. It turns out that when everyone say the interior Antarctica is very seismically quiet, it's actually not. We actually were able to see things. The reason they think it's quiet is there was only one station there. And when you only have one station, when you see something, you're not sure what's going on. As I said in the California case, right? But when you have a dense array, suddenly it's easier to pick it up. This was an earthquake, magnitude 2.4 earthquake, 300 miles away from the South Pole, right? The conventional seismic station, of course, detected, but with only one sensor, they cannot tell what's happening. But this was detected on the fiber. Now you have thousands of sensors. Now we change it to every 2 meters. It is too much data for us. And you can see the S-wave, and you can see they were different from channel to channel. It's actually a little bit early on this end, later on this end. Automatically tell me the earthquake was happening, on which direction of the cable. So with this kind of array, we can start to make more sense of the signals and figure out what is the actual seismicity in Antarctica. And this seismicity can be used to study the structure of the ice. We actually detected ice quakes as well, maybe not too surprising. This was a magnitude 0 earthquake, ice quake, about 8 miles away. The conventional sensor detected, but we can see how the wave propagated. You can even see these little details in the back here. We can see why it looks complicated, right? If you don't have this information, you can almost never figure out what those waves are. The most interesting one or surprising one we see was this thing called firmquakes. You can see this one is almost as clean as when I stack all my 1,000 strikes of hammers. Like, what is this? It turns out these events are called firmquakes, happening very close to the South Pole Station. And it only happens when the temperature becomes really cold. And you say, like, South Pole, you're already cold. How cold can you be, right? Well, once in a while, they have really cold days. So they go from minus 60 F to almost minus 90. And sometimes go to nearly minus 100. And it's a sharp change, so there is a cold front suddenly move in. What we think is happening is so cold that the ice start to frack. So they start to have cracks in ice. The ferns start to open up, right? Like even snow cannot bear that cold. And in those cold days showing at those bands, there were like hundreds of cracks just popping up in the snow, and each one of them producing a signal like this. And we are now in the process to see what we can learn from these signals, because they happen, right, regularly in Antarctica. And we can use them to study the base of the structure, see if there's anything is changing over time. So I hope by now I have convinced you that like the South Pole array is really a big success. We go from this conventional way of doing it, multiple people, a few sensors, to 2 people, thousands of sensors right away. And all the amazing data I was able to show you is only possible because of the density of the sensors, right? Like you can get so much more insight because now the sensors are a few meters, a meter apart from each other. You can really look at this whole field of waves, kind of like animation to see the wave propagating. So I believe that to me means we need to do more of this. We need to get this thing going everywhere in Antarctica, maybe even in more interesting places where the ice is moving a lot faster, where you have a lot of more response to climate change. After all, South Pole was pretty interior of Antarctica. So this is the map of Antarctica fibers. There's nothing. So I just randomly grabbed one. I already used up the single fiber on the entire continent. So my students and postdocs now, they have to do the harder work. The low-hanging fruit, I already grabbed it. So they would have to deploy their own cables. Well, how do you deploy cables in Antarctica? Well, these are pretty creative engineers and students. They made this device that we were just about to test. It's like a spool of fiber with a plow, and you drive over there, and it will dig a trench, and the cable will just go behind you. And we hope we can one day go just drive a piston buoy over Antarctica, and it will deploy tens of kilometers of fiber just behind us and the barrier. They were just starting to test this 2 days ago, and we're going to run more tests, finding an ice place, and then hopefully we will bring this to Antarctica once it becomes more mature. We also would need to produce DAS unit, the interrogation unit, that's a lot lower power, right, and smaller, so we can more easily run them for longer period of time. So there's a lot more work we can do. We believe we can make a bigger contribution there. What are the other places you think this technology could contribute? Well, it must be a place conventional ways of doing seismology is hard. One of such a place is in the ocean. In the ocean, we have relatively few seismic stations. It turns out these days there are a lot of telecommunication cables out there. There was actually a total like 1 million miles of fiber that's already deployed, And as we all, use more and more data, this number just keep growing, right? And this figure, the red line, are showing all the current fiber optic cables in the ocean. If we can tap into this network and turn all of them into sensors, that would totally change how we do seismology for the globe. We will be able to see events happening on the sea floor, and we would also be able to sense deeper corners of the Earth that we couldn't image at the moment using stations only on land. Turns out the DAS technology we were talking about right now only can use about 100 kilometer of cable. So this is 1,000 kilometers of fibers. So we have to develop newer technologies. A few years ago, I actually did one of those technologies using so-called polarization. We were able to turn this 10,000 kilometer long cable from Los Angeles to Chile to a gigantic sensor, and we were able to detect dozens of earthquakes during the time of operation, right? But this is not the perfect technology. It does not tell you where the earthquake happened, so we are still trying to develop newer technology on that. So there's a lot of technology development trying to make use of those cables as well. Another place that would really benefit from this kind of dense array is the moon, right? Like we have even spotter arrays there. Only in the Apollo time, we had a few seismic sensors there, then they are separated, hundreds of kilometers, 1,000 kilometers from each other. There was never a sensor like a very dense network on the moon. And of course, it's very challenging because each one of those sensors needs to survive a very harsh environment. But now with the fiber sensing, it's possible because the cable can be engineered to survive a very harsh environment and only have to take care of one end of it. Right? So the trouble right now is like, how do you deploy a cable on the moon? I want to find a contractor to do that. But one way to do it is like, for example, this is the image I steal from Professor Greg Helliland, astrophysicist here at Caltech. He wants to do this far side project because they want to deploy a radio telescope on the far side of the moon. And they would have to deploy a cable as well. So we could join force and use the same cable. He can look into the sky, I can look underneath us, find out how the moon evolves and what does that tell about the history of Earth. Finally, I want to come back to California, right? I hope this story about what we did in South Pole would convince you that there is really a lot of potential in California to do the same thing. We so far only use a very small fraction of the existing cables. And there's a lot more we can do, right? If we can turn all these cables into a seismic array, thousands of times more than what we have now, we would have much better subsurface image, like what we did in the Long Valley area. We'll be able to image how earthquake rupture goes. And we can also provide better earthquake early warning. Earthquake early warning is all about catching the earthquake early on, send you alert before the wave strikes you. Right? You have more sensors, you have a better chance to catch them early. In particular, there are all these cables going offshore. And if earthquake happens there, currently we don't have a lot of stations to warn them, but with cables we will be able to do much better, right? And the current technology can already do that. Of course, there are challenges, but we hope we can move in that direction. There is a lot of potential in this. I want to end the talk with this picture I took. This was on the last day when I was like the first away from the South Pole Station. I think I'm about 6 or 7 miles away. It doesn't feel very far, but it's far enough that you turn back, you couldn't see the South Pole Station anymore. Like there's nothing out there that gives you a sense of direction, okay? And the only thing behind you is your track. If I don't have a GPS, I would not dare to go. I would go completely lost. And at that moment, you look at the view, it's a gloomy day, and you think about the 2 miles of ice underneath you. Like you feel pretty small. This is such a gigantic, just vast openness in front of you, right? And you feel small. But at the same time, you think like human can have such an impact to this really remote place. And the response of this ice there can have an effect back on us with the sea level rise for our coastal communities. So I think we really got to protect our planet. Like this is the Earth Week, right? We really got to take care of our Earth. And I hope seismology, which used to be considered earthquake-focused science can make a contribution here too. We now have the tools to easily deploy dense arrays in this kind of extreme environment and figure out what's happening underneath. Hopefully that will contribute to our understanding of the physics of ice and help us better forecast sea level rise in the next decades. With that, I want to thank you for your attention, and I will take any questions. Thank you.
Thank you so much for telling that story. You brought such a feeling of fun and play to what I am sure was actually quite brutal
Hard
field
work, too.
conditions. Definitely. So I have to ask, how often do you encounter this interpretation of seismology where it's just earthquakes? Because I realize that in listening to your talk today,
Right.
I have personally changed my conceptualization from earthquakes to listening to the earth.
Right, yeah, it's very common. Every time people were asked about when is the next earthquake, right? When is the next big one? But really, earthquake science is really about listening to the earth. And there are a lot of information there. Like, we are listening to each other. There you can figure out a lot of things.
I never thought of the earth as a musical instrument before, but now with your data, I do.
Yeah.
Okay, we have a lot of questions, so a lot of them are about Antarctica. So for those of us who can't travel to Antarctica, are there local places where we can experience some of the phenomena that you talked about?
Right. We sometimes encounter this problem when we want to test our newest technology, because it's hard to propose to test the technology in Antarctica. So we find the places, if it's a relatively small experiment, sometimes we go to high mountains, right? Like even close to ski resort maybe. But sometimes scientists go to Alaska to a lot of testing. Iceland is a good place. And the next big one would be Greenland, right? So different levels of complexity in logistics. Well, the plow I was showing you, we were actually going to test it first in Iceland first, before we can bring it to Antarctica.
So if you're a student with a yen for traveling to cold places, what program should you look for? The specific question is, what should I study at Caltech so I can go to the South Pole?
Oh, surely in the GPS division, right? So there are actually a lot of polar research programs within their division. Mine is the Seismolab. We do a lot of satellite imaging and also this kind of field work for the polar areas. But there are many other areas, especially like the environmental science and engineering. They regularly go to the oceans around Antarctica to study the interaction of ice and the ocean there. Yeah.
So what are the next steps for these data? What is the next type of scientists that are going to be able to get more information using their own area of interest and research?
You definitely don't have to be a geoscientist to contribute to this process. Some of the biggest challenges are data processing, computing, right? Like one experiment, we were taking 200 terabytes of data. And it takes a long time to process all of that. And we rely on artificial intelligence to help us to speed up that process. So if you are a computer scientist, or you just know physics, right, knows how to interpret the different physical processes, well, welcome all these students. Turns out a lot of geophysics students coming from very different backgrounds to us.
So I have a question. Can you tell more about the physics of the fiber echo?
Yeah. So, of course, when they manufacture the fiber, they want to make it as clear as possible. So the light will propagate through, as best as they can, so it can propagate far away. But the way they do it is basically taking like molten glass, to put it simply, molten glass and stretch it. They call it pour the fiber. In this pooling process, the fiber is not going to be exactly uniform. There are some places a little bit denser, some places a little bit less dense. And that's enough to reflect the light back. We're not talking about the echo that's very strong. The echo was 1 billionth times the original light that goes in. So it's a very small amount of light. It's just the technology is so good that you can detect them. This is the same way as LIGO people detect change of their mirrors. It's the same processing, but we used for this particular purpose here.
How is power generated at the South Pole?
Good question. It's actually amazing how they operate the South Pole Station. It's really a privilege we have a station there to do the experiment. The South Pole is a large station, and the supplies, it's not enough to bring them by flights. So every year there will be a group of drivers driving tractors, dragging sled, and they are going to drive for 1 month from McMurdo Station all the way to South Pole Station with fruit, with food, equipment, and fuel. And so the power station was actually powered by fuel, gasoline. And that's how we provide all the power we need. And it's such a remote place, the sun is at a pretty low angle, so the solar power is not going to be enough for that. And there is a half year of winter, like it's just dark.
That's one of the things you learn about energy sometimes. Being stored in a molecule is just the best place for it.
In this case, it definitely need to be.
Would you recommend an ice cream enthusiast to spend some time on the South Pole for permanently unmelting ice cream experiences?
You should ask my daughter about that instead of me. Turns out there's food choice at the South Pole was pretty limited. They have the best chefs in the world, meaning that from all those food they bring from McMurdo, thousands of miles in there, that's sustained for months, right? The choice is very limited in terms of what fresh produce. And they just can figure out smart ways of doing things that make every day the food is a little bit different, and sometimes there are surprises. So I'm just admire what they do there. But I think in terms of ice cream, they only have chocolate flavor. No. That's the only one they have.
All right, so you better like chocolate if you go there. Shifting a little bit from Antarctica to a little bit closer to home, can you describe the process of placing the sensors in California?
Right. So the conventional sensors, when they do it, it's actually pretty labor intensive. Like you have to dig a hole to bury the sensor, and you have all this equipment. So with the fiber sensing technology, it actually has been pretty easy in the sense that the fiber already in place. Every tens of kilometers, they have a little house. It's called the node. And that's where they have also telecom equipment with power and AC and everything. And when we got access, thanks to a lot of big supporters of this program, we got access to that node. We just bring the machine there, plug it in, that's it.
How far underground is the cable placed?
The cable is usually deployed a couple of feet underground. And that's usually enough for us to sense the Earth's motion with no problem.
And is that the same for the cables that are placed under the ocean as well? Or what's the depth there?
That's a very interesting question. So in the ocean, it's a long cable. It's a very expensive process. So they would only dig a trench near the coast in case a fisherman was trawling on the bottom and break the cable. But once they get in a deep ocean, no one's messing with it. They just lay the cable on the seafloor to be fast, to be efficient. Yeah. So it's very different in different areas.
And I have to ask, what is the future of earthquake detection in California or beyond?
So we can do a lot better already, and we are keeping doing better. If we can realize the vision I have for California, we will be able to detect every earthquake with 1,000 times more sensors. I often make this comparison with astronomers or astrophysicists. They sometimes send an expensive telescope to space. And every time they develop a new telescope, the stars becoming a little bit more clear, right? A fuzzy image suddenly becomes like crystal clear. That's the process we are going through, okay? It's not about detecting the tiniest and tiniest and tiniest earthquake. It's about the bigger ones or the moderate sized ones, like magnitude 3, 4 ones, you felt it. In the past, we think of just a patch broke, that's it. But there's actually a lot of details in that. Earthquake, unzip a fault in a process is not instantaneous. That physical process is really important. We used to don't know about that. We only know the rupture process of a magnitude 8 earthquake, magnitude 7.5 or bigger, I would say, right? And only if in California you can see something down to magnitude 6 levels. But with the fiber network, if we can fully deploy it, every magnitude 5, 6, even magnitude 4 earthquakes, we will be able to, just like having a new telescope, suddenly the image will become a lot more clear. We will be able to see how they ruptured. We will figure out their physics. I think that's the promise we're going to make with the new array. It's going to be a different way of looking at earthquakes completely.
So is the moon known for its seismic activity? And if not, what do you hope to learn from sensors on the moon?
I always wanted to go to Antarctica. I got to go, and now I really want to go to the moon. So I'm not sure about that yet.
Division of planetary science, geology and planetary science students.
So the moon is a seismically much quieter place. We already know that from the Apollo time. Doesn't mean it's completely quiet. There is still a lot of unknown about, like, is there any tectonism, meaning like some activity still going on inside of the moon. During the Apollo time, the sensors are so sparse, you can only detect the big ones, and they're pretty rare, right? So I hope using denser arrays deployed on the moon, you're going to be able to see smaller events on the moon. And with the denser array, you can also figure out where they are. It's very hard to locate them in the past. But now with the denser array, we can have like an antenna. We can look at it in different directions. Oh, where is this one coming from, instead of a single sensor? So we think we can reevaluate, let's say, the seismic activity of the moon. And hopefully that also tells more about when the wave travels through the moon, tells more about the interior structure of the moon. Like, what is the history of evolution on the moon? How many impact has happened in a certain place to completely mess up the crust there, right? Those are the questions that have a lot to do with comparing the evolution of Earth and the moon, to understand our origin on Earth.
So how far away are we from really taking this technology and this research to like further extraplanetary locations? Will we eventually have rovers that are able to lay the cable and detect the seismic activity on different planets? Or where's your, besides the moon, where are you going next?
I would be pretty happy to go to the moon.
Okay.
Just as a start. But it's hard to predict the future, how fast we can. Maybe it's faster than I thought, maybe it's slower than I thought. But the key is to take the first step, is to realize we think this is the vision, it's the right thing to do, and we're going to start somewhere. I think Caltech is the perfect place to do that. It's a very high-risk thing to do, but we think it's the right thing. And at Caltech, we have the capability. We have scientists. We also have brilliant engineers. We also have JPL. Bring these things together could allow us to make the first step, to demonstrate how this thing could work. And hopefully, sooner than we expect, we're going to be there. And the moon first.
Moon first.
Moon first.
Then maybe Mars.
Yeah.
To bring things a little bit back to Earth, because it is Earth Week, do you think that we could use the same technology to detect large animals moving, like elephants or animal migrations? Same type of monitoring?
Yeah, it's already been done. Okay, but it's mostly, right now, I think it's in the ocean. Okay, I can detect cars, so why not elephant, right? So, for sure. But at the same time, in the ocean, there are cables, and sometimes when we run these arrays, we can actually hear whales. Sometimes they were like miles away from the cable, and we can still hear them call. And you can even recognize like the difference between different whales. So it's actually a wonderful way of maybe studying the marine mammals. Yeah.
If you could place a fiber optic cable with a DAS system anywhere in this world, not the moon.
Not the moon.
Where would be your next like high priority location?
Oh my God, that's
Or
hard.
dream location, maybe you just like want to go to Tahiti.
Yeah, that's hard to pick. So I think there, go to a more active place in Antarctica would be the next target. It's hard to do, logistically, technology-wise, very challenging. I hope to have another one that can run there continuously without people attending it for a long period of time, so we can really see the dynamics of ice in response to all the forcing from outside, either from the atmosphere or more likely from the ocean side. That's just an important science question that we have very little detailed understanding about.
It seems like it takes a certain type of personality to be able to do this type of field work,
Right.
or at least to get the precious data enough to be
Right.
able to analyze back in the lab. Like
Right.
rock climbers have a way of classifying fun. Like type 1 fun would be Tahiti. Type 2 fun is the kind of, it was fun after the fact, but not during, so kind of like grad school. And then type 3 fun is like not fun at all. So what, other than tolerating type 2/3 fun, what are some other qualities that you would look for in a graduate student or in a scientist
Right.
in this area? What makes someone successful?
Yeah. I will say the curiosity might be the most important piece here. You actually don't have to like field work to do it, right? Like the drive, the curiosity that you need to learn about this, and you need to design your experiment, maybe design a device that doesn't exist yet to actually get to know the answer. That's kind of the most important piece. The South Pole trip was actually the biggest trip I've ever done. Like I've never done anything as big as this, but with a lot of drive and curiosity to make sure it's successful. I think it was done nicely in this case, with a lot of luck as well, right? But sometimes you have to make peace with yourself. We tried our best. This is what we can do, right? The drive and have inner peace to do the science.
That sounds
It's a
little
good
bit
thing.
harder than it sounds.
Right.
What was the hardest part of this type? It could be the Antarctica trip. It could be other types of research projects that you've done. But
Right.
what has been the hardest part of this type of research?
Yeah, I would come back to the inner peace point, right? It's hard to plan everything. It's impossible. You don't know what's going to happen. No matter how well you think you have planned, something always go wrong. And a lot of things will go wrong. And you just have to focus at the moment and try not to be frustrated and try to focus on the problem itself. I say we just have to solve the problem. And this happens in all field work. And probably also for all graduate study as well, like even if you're doing lab or other type of research. So I think that's the biggest lesson I learned from the trip. It changed me in that perspective.
What was the most fun? Was it the hammering?
It's explosive, right? Before realizing it doesn't work.
Getting to blow something up.
Yeah. Well, if you do geophysics, you're going to get the opportunity.
Well, thank you so much for sharing your story and for showing us that brute force can sometimes improve your data.
Yep.
Who knew? And definitely, I think you'll be joining us outside for tea and coffee. So if there's additional questions that didn't get asked, please feel free to join us outside in tea and coffee. And don't forget to come next month for the next Watson lecture, because I hear it's going to be very special, and Carver Mead will be our speaker. So thank you, everyone, and please have a wonderful evening.
Thank you so much.